Good day, everyone. My name is Robert McGinnis, and I'm a Senior Account Manager at Mechanical Simulation Corp. I have represented our car sim, truck sim, and bike sim products for the last 12 years. Working in mechanical simulation has been a very satisfying experience since I know our technologies are used every day to invent features that make vehicles safer for drivers and pedestrians alike. I would like to thank UKI Media for inviting mechanical simulation to present at this exciting event and helping me convince my boss that this in-person event is being held in Hawaii. It would be great if someone could make me a Photoshop image that shows me making this presentation under a palm tree. I considered several different titles for this presentation, since there are so many ways to approach the importance of high-fidelity vehicle dynamic simulation. So instead of coming up with the best presentation title, I decided to put my energy into using popular culture references to help illustrate how simulation is used and perceived in our industry. To help make this more interesting, the person who sends me an email itemizing the most movie references used in this presentation will be sent a $50 Amazon gift card. The basic thesis for this presentation is that high-fidelity vehicle dynamics is important for all levels of vehicle simulation. Since I've been damaged by watching thousands of political commercials in the last few months, I must repeat myself. High-fidelity vehicle dynamics is important. I want to begin with a slide that I usually discuss at the ends of presentations. The top half of the slide is a modified slide from NVIDIA that shows how different fidelities and complexities of simulations are effective in different domains and different parts of the AD product design process. The main takeaway is that physical testing is important, but should consist of the fewest number of miles driven due to cost, lack of easy repeatability, and time constraints. The blue trapezoid on the bottom shows how vehicle simulation is, of course, not only limited to autonomous vehicle and ADAS features. The world has been simulating vehicles for 40 plus years, so it makes sense to leverage those technologies as we move forward. I'm going to start at the beginning of modern time, let's say the 1960s. Although simulation is not completely new, it started to expand from the military and aerospace industries as computers and programming tools became more available. The process of obtaining useful simulation results was slow because it was a time when someone first used the phrase garbage in, garbage out, indicating that if you feed bad data into good models, you will not get usable results. In a classic chicken and egg scenario, people were quick to realize there was a lot of work to be done to generate high quality data to feed improving vehicle simulation models. Another concept from the late 60s is that of the physical twin. Of course, this made the most sense for aerospace programs that had large budgets, but also had analogies of what we now call mule vehicles. These were extremely useful, but also exposed several flaws that limit their usefulness as complete engineering tools. For all the flaws in this concept, the physical twin did establish an aggressive set of goals for the industry to reach. As we move into the 70s, computers are now gaining in popularity and starting a plot to assume complete control of our planet. On the plus side, the promise of computer aided engineering and simulation is becoming a reality. This sparks the creation of several industries focused on virtualizing the automotive industry. Highlighted on this slide are some early car sim animations and a model of an early tire testing machine. Into the 1980s. Same story, but accelerated as CPUs are starting to appear in cars and 8-track tapes are being replaced with cassettes. We are also getting to the point where many engineers have home computers and spreadsheets are becoming popular. Late 1980s. Now that simulation is becoming mainstream, it is good to check in with engineers who went back to business school and are starting to focus on V curves, time to market issues, and synergistic partnerships. It's clear that virtualization and simulation is the only way to keep up with the rapid increases in technology, global competitive market forces, and regulatory demands. I'm now going to take a break from history and focus on considerations for evaluating vehicle simulation technologies. To be honest, I didn't understand this slide at all. Our engineers forced me to include it. Since this slide alone could be a source of a 2-hour presentation, I will summarize by stating the importance of understanding the underlying assumptions built into your simulation tools and make sure you are able to provide it with the data the models require. We have now reached the future. Several companies are suggesting that a multi-physics model capable of simulating multiple domains at the same time is the answer. For small products that operate in rigid conditions, this makes a lot of sense. However, when considering something as complex as an autonomous vehicle, developing and maintaining such a model is not reasonable with current technologies. There are reasons most OEMs use 3 or 4 different tire models, multiple powertrain models, and different HIL platforms to do their testing. To properly balance the computing time, simulation fidelity, and scenario creation equation, different technology combinations are still needed and will be for the foreseeable future. Now I would like to get into the specifics about how car sim and truck sim are designed with a philosophy to meet our customer needs that I have laid out in previous slides. Since we want our models to run everywhere, we strive to have our solvers run much faster than real time on laptops that are typically assigned to engineers at OEMs. This assures customers that their desktop scenarios can run on hill platforms and still leave plenty of time for other co-simulation activities. We also strive to provide tools that will run on all platforms, so customers do not have to change their data and models as they progress from software in the loop to model in the loop to hardware in the loop. Data and models may get more sophisticated as you move to hardware in the loop, but they don't have to. To accomplish these requirements, we work hard to only include the degrees of freedoms that are essential for vehicle dynamics. If more fidelity is required, customers can add them with co-simulation tools, but they need to evaluate the entire tool chain if they expect it to run on hardware in the loop. The basic layout of our vehicle sim products, which include car sim, truck sim, and bike sim, is a modular architecture that includes models for every vehicle subsystem. These modules include obvious items like brakes, powertrain, and tires, but also include a 3D road model, vehicle payloads, and even traffic vehicles and pedestrians that can be scripted with simple motion commands. The product includes a graphical user interface that provides intuitive screens for engineers to import data or enter data for each subsystem. It also includes powerful video and plotting post-processing tools. Once a simulation is ready for execution, it can run from the user interface or it can be transferred to an external simulation engine such as Simulink, Constellation, or the Unreal Engine for use in a co-simulation toolchain. The solvers run on Windows, Linux, and most cloud computing platforms. As we start to work our way into discussing tool chains and simulation platforms, this graphic shows area where our customers and partners have added technologies that customize our vehicle sim products for specific applications and domains. In many cases, mechanical engineers with expertise in a certain area, let's say steering or braking, add specific features that they believe are essential but would overwhelm or not be valuable to other engineers. These techniques also work for ADAS and AV engineers who can easily add active and nonlinear controls or specific sensing technologies into the platform. The top part of this illustration shows the different model changes our customers have integrated into CarSim, and the bottom half shows the tools that can be used to execute the integration. Some of these tools are built directly into our products and do not require any external tools. Others can be integrated with a simple Simulink or Python model. Finally, some involve complex tool change maintained by a team of hardware, software, and application engineers. When we introduce the idea of using simulation tools for autonomous driving, we start to see a separation of teams within our customer base. Our traditional users are very familiar with single vehicle simulations and have invested billions in simulation labs suitable for launching a new vehicle and all of its build variants. When looking at supporting new ADAS technologies, these customers seek incremental improvements to their existing simulation tools. I always like to show this video since it highlights a few situations that are not typically discussed for autonomous vehicles. Both engineering disciplines are positive that simulation is essential if we are going to reach our autonomous driving goals. As expected, each side also has a tendency to search for the simplest simulation technology to represent the domains they are not familiar with. And they are not wrong. Mechanical engineers developing controllers are happy with the simple threat target list provided by the vehicle's suite of sensors and fusion algorithms. At the same time, autonomous driving engineers are perfectly happy with the bicycle model of the vehicle. When we evaluate the results of a single simulation or a suite of hundreds and thousands of simulations, we need to establish a set of rules to measure each simulation run. Depending on the outcome, engineers need to evaluate metrics such as variance from the expected path, binary collision avoidance, and the minimization of collision energy. Each of these metrics require both accurate vehicle models, but also a faithful representation of the sensor suite. The answer is nobody knows. What is known is that lots of simulations using different simulation fidelities will be required. To make things even more interesting, the importance is highlighted when we must consider more nebulous factors, such as how fleets of autonomous vehicles and traditional vehicles will interact, and how the ride frequencies of a single vehicle will affect passenger sickness. Now we come to the point where the two engineering disciplines must collaborate. The mechanical engineers understand they need to consider vehicle sensors, multiple traffic vehicles, pedestrians, and a wide range of weather and lighting conditions. The software engineers have to deal with 2,000-pound vehicles with dozens of nonlinear interconnected systems that they must control within a precision of a few centimeters. The first vehicle feature that made this collaboration requirement obvious is forward collision braking. In the words of the world's greatest modern philosopher, George Costanza, this is when the worlds collide. In the spirit of nobody has time for inaccurate results, this slide shows a few of the effects that are overlooked or just incorrect when simple vehicle models are used. All of these items use vehicle pose estimation errors or simulation environment that cannot scale for next generation features. This slide provides some of the more details about what could be missing with less sophisticated vehicle dynamics models. If any of these effects or technologies are ignored, the vehicle's position, velocities, and accelerations will have errors that will only be detected when hardware in the loop or physical testing begins. This is the opposite of the previous slide because it lists the features that you do get with the high fidelity vehicle dynamics model. One topic we have not discussed yet is the regulatory and compliance side of autonomous driving. Euro NCAP is a good start to this effort. This standard provides a great set of regression scenarios that can evaluate autonomous vehicles in a broad spectrum and also provide a scoring matrix that we all desire. This is a good example showing how a complex test suite can be built with a single simulation tool such as CarSim and then extended with Simulink models and physics-based sensor models. An exciting new technology we are rolling out and improving in every version is the ability to run multiple high-fidelity vehicles in the same simulation environment. This is becoming essential technology for applications such as commercial vehicle platooning, intersect navigation, and evaluating collision mitigation strategies. I think we all understand that one company cannot develop a complete suite of AV simulation tools without leaving huge coverage gaps. The industry works hard to ensure interoperability so engineers can choose the most appropriate tools for each simulation domain. For this reason, we have a partner programming involving some of the most prestigious software and hardware companies in the world. One of the partner technologies we are excited about is the Unreal Engine, since its development is driven by the gaming industry and it's optimized for modern graphics cards. To support this technology, Mechanical Simulation has released a car sim and truck sim plugin that our users can download from the Unreal Marketplace. The plugin allows multiple high-fidelity vehicles to drive directly on Unreal terrains. We also have developed an FBX terrain import feature and built different co-simulation interfaces for simulate controls in a variety of different sensor and traffic models. Another new partnership we are rolling out this year is with NVIDIA's high-end DriveSim product. To my knowledge, it's the most powerful HIL system in existence, since it provides the computing power to simulate physics-based sensors, high-fidelity vehicle dynamics, and complex traffic. The technology also uses state-of-the-art AI algorithms to automatically curate hundreds of simulation scenarios based on a single input. I would like to thank everybody for listening to this presentation. I will be online for the next 15 minutes to answer any questions you may have, and you can also contact me at rmcginnis@carsim.com. Aloha.